Howdy everyone, Dr. Regev here. Now here is a demo of a radar simulation. It's a live range profile simulated, a single target at 80 meters and white noise type simulation. And we are going to see how different discrete as well as continuous probability distributions are affecting our radar performance. And this time we're going to dig into the miss probability. The miss probability is 1 minus the detection probability. It's the probability that we miss a target. Okay, let's run the simulation. You can see here the simulation is running. It's running now. It's a live simulation. This is the target here. Sometimes it misses, doesn't pass the threshold. Sometimes it does, and we detect it. Okay, what's the rate? 38% of the time we miss it. Okay, how does this actually come to pass? The PD is calculated from PFA and the SNR, the false alarm rate and the SNR, and PMIS is 1 minus the PD. Okay, and you can see here now I populated all of these distribution. The solid lines is the actual theory, and the histogram is the empirical that you actually measure instances of misses from the data that is running. We are running it on 5,000 trials, okay? And we are calculating all of this data. So for example, geometric distribution, that's the twin brother, the discrete twin brother of the exponential distribution. That's the geometric distribution is PRIs, pulse repetition intervals, or pulses, or chirps, until the first miss. And you can see here that this is, as expected, is distributed geometric with a mean of 2.6. Okay? Binomial, we ask ourselves how many misses in 50 pulses. So this will be a binomial distribution. It's N choose K is driving it, if you remember that, from probability theory. The Pascal distribution. Pascal distribution is asking how many PRIs until, for example, the third miss. We can play with the Pascal parameter here. For example, can increase this to 4 misses. Okay, and then we will probably wait more time. Let's increase it to 8 misses, and you can see that the Pascal distribution shifted to the right. Okay, and the mean of the Pascal distribution is 20.8. Now, these three are discrete type distribution, all based on observing and counting Bernoulli trials, success and failure trials. In this case, we treat a success as a miss. Okay. Obviously, we would like to, in radar system engineering, in the Pascal distribution, we would like to shift the Pascal distribution to the right as far as possible. Right. So when we are designing a radar system, we are taking all of these into account. Now, I promise you that you haven't seen this type of analysis for radar systems before. The exponential distribution, other than the actual absolute value squared noise that we see in a real value imaginary value type Gaussian noise, when you square it, when you add it together, you get an exponential distributed noise. And in this case, the exponential distribution is actually what is the time, the actual time until the first miss. And you can see here that the measured time is adhering to the theory, and the mean is 156 milliseconds in this case. So it's 0.156 milliseconds. Sorry. So you can see here that we have a very nice simulator that will show us how we can quantize and quantify qualitatively and also quantitatively the radar detection parameters and the radar detection performance, other than ROC curves and all the good stuff that we already are studying in the courses in the academy. If you haven't joined the academy yet, please consider doing so. Go to academy.drneregev.com, and if you have any questions, just reach out to me on LinkedIn or in my email, and I will do my best to answer all of your questions regarding the academy and the services that me and my company, Alex Zero, provide. All right, guys. Until next time, Regev out.